So, welcome to your expert workshop in social cognition. My name is David Von Becker. I publish as D. Von Becker. I go by Von. And I am an evolutionary psychologist, but I was trained as a cognitive psychologist, and most of my publications are in social psychology. I also dabble in neuroscience, and one of my master's advisors, my primary master advisor, was one of the members of the PDP group who are the folks that are responsible for a lot of the AI in the world now. The transformer descends from something um, called a recurrent network, which came out of this group. So I have my hands in a lot of different parts of the field. And what I want to do in this expert workshop is something a little bit different than what you typically get. I would like to, even though this is only worth half of a class credit, um, I would like to give you some skills and some tools that could unlock a lot of possibilities for you. Now, I will point out that it's also atypical to be doing this workshop outside of a week's time frame. What I'm doing instead, and what I've done for the past several years as I've been teaching this, is I meet with you a couple of times, like we are this week, introduce the general ideas, give you a few assignments, give you some time to really absorb not just the readings that you might be focused on, both the ones that we're all going to read and the ones that you might need to do for your own personal projects. But I also want to give you a chance to learn two important practical skills that are going to set you apart, um, whether it's in the academic world or on the job market. And so that's why we're having these early meetings. Then there's going to be this gap. You'll have another component of the expert workshop, and then we'll get together at the beginning of June, and we'll have some in-person meetings, and we'll really dig into what is possible in the world of social cognition, designing experiments to explore social cognition. Um, and so the structure of the class is a little different than what you might typically get. It's also the case that the deliverables are probably going to be a little bit different than what you typically get. And this year, I'm going to have to change that even more because there seem to be more of you. And so, in order to make the grading and the assessment something that is feasible, then I'm gonna have to think about how we structure things for the final project. So, if you read the syllabus, you know that the final project can, at this point, I was saying it could either be something that's more conventional, like a paper that describes what you want to do, or an actual execution of what you want to do. I think we're going to lean toward the latter. It's a much better skill for you. And so then the question becomes how do we make this something that is accessible in a reasonable amount of time? Um, so I'm going to think about this uh, in between today's lecture and Wednesday's. Today's lecture is going to run about 2 hours, even though we have 3 hours. At the end of the 2 hours, I'm going to send you the link to two Qualtrics surveys. These are surveys that will take maybe 30 minutes for you to do, but you probably want to take a little break in between. And the surveys not only ask you questions about who you are, so that I can get a sense of the kinds of research interests you have and the background that you have, but they also will contain several experiments, and they'll give you a sense of the kinds of tools that we're going to try to unlock in this course. So it's a bit different, but I think that by the time we're done, you are going to find that this class liberates a lot of potential, sometimes potential that you didn't even realize existed. So before I begin, um, I just want to give you a chance to ask some general questions. Uh, is there anything that I'm missing? Is there a big chunk of the cohort that's not showing up today for some reason that I don't know about? One of the many quasi-religious holidays that seem to still be on the books in the Netherlands.
So I think our group is just about 30 people. So I don't think we're missing too many from our social psychology class.
So maybe oh, it does look like a lot more people have shown up than when I was last looking. Okay. Um, okay, thank you, Emma. Um, well, fortunately, this will be recorded, and so the folks that are missing, if there are people that are missing, can watch that. I also have a few other folks that may be joining us that are not part of this cohort, but will be helping. So a graduate student, for example, that will be helping with some things, just to make my burden a little bit easier. I should also start off by noting that what we're doing in this class is a very abbreviated version of what I do in a Foundations of Cognitive Science class that I teach in the Human Systems Engineering department here at Arizona State University. Um, we cover a lot more territory in that class, but are some of the deliverables are quite similar. Um, and over the last several years, I've refined this, and so I think that it's going to be not only a fairly well, it's going to be an eye-opening experience, but it's going to be more straightforward than you might think at the outset. When you get a sense of what I'm going to be asking you to do, you might go, "Oh my gosh, I had no idea I signed up for that." But trust me, um, every one of you in this class is capable of doing everything that we're going to be doing in this class. Doesn't require a lot of statistical uh, knowledge, and I know your statistical training. It's actually quite rigorous, so that's not going to be a problem. The real thing is just to open your mind to the possibility of what designed experiments can be. So, without further ado, let me share the screen and we'll jump over to a PowerPoint. I should also note, just really quickly, that it's 4:30 in the morning for me. And while I'm pretty alert, I am having a bit of an allergy problem, which sometimes happens when I get up too early. And so I might have to take a break if I start sneezing. And we will take a break about halfway through this lecture as well. So let me share the screen. And if there are questions, I'm not going to be able to see the chat screen right now, because I have to minimize it so I can see what I'm doing on this. So I'll give you a chance to interrupt and ask questions at different points in this. All right, so I am, as I said, Dr. Von Becker at Arizona State University, and this class is about social cognition, which I think of in a very broad way. But for the purposes of this class, we can think about it as the detection, encoding, and representation of social information. And we detect this information, we encode it into memory, we represent it in knowledge structures. All of this is done in the service of what we call, in my lab at Arizona State University, uh, affordance management, the management of affordances. So, from a theoretical perspective, we're going to be talking about what affordances are. This is a concept from James Gibson, but it's much more broadly used now. And by the time you're done, you'll not only have some practical skills, but I think some new theoretical levers to apply to whatever the research interests that you have are. Social cognition broadly blends the questions of social psychology with the methods of cognitive science. These methods are incredibly powerful. And one of the things I want to do is really focus on the methods because there is an incredible potency and elegance to how they can reveal things like how we detect social threats and opportunities, how we learn and remember things about social groups and individuals, the kinds of categories that arise about social groups and individuals. And those categories include things like stereotypes. Stereotyping and prejudice is a really core applied area in social psychology and social cognition, especially. And in order to understand how those stereotypes arise, we have to start understanding things about how we categorize things more generally from a cognitive perspective. All of these influence the inferences about what others afford us. When I encounter someone on the street, even if I'm not overly motivated to think about them, automatically at some low level, I've got all these mechanisms in my mind that are trying to figure out, is this person in danger? Oh, they're sneezing. Are those allergies, or might they have a disease that I could catch? Those are negative affordances, disease, aggression, but there's positive affordances too. You meet a new person in the line at the grocery store, and all of a sudden a little voice in you starts saying, "Oh, this person is attractive to me. They might be a benefit. I should reach out and talk to them. I should say something and introduce myself." So the inferences that we make are often driven by these somewhat unconscious parts of us that often have roots that extend back into the Stone Age, roots that are designed to make sure that we maximize the benefits that others afford us and minimize the costs that they might pose. The core of social cognition is thus going to be the adoption of the methods of cognitive psychology to explore these kinds of questions. I'm going to go further, though, in a theoretical sense, and say that the missing heart of social cognition, which, social cognition really started maybe in the 1970s. You can find some precedents a bit earlier. But the missing heart of social cognition, and this is true so often of other things in social psychology, has been the co-evolutionary backstory. The fact that we've got these affordance management systems that are conditioned not just by the things that we've learned from our parents as we grow up in school, the things that we've indirectly learned from the cultural stereotypes that are so interwoven with the kind of social media environment that we're in, that we're often not even aware of them. Beneath all of these proximate influences on how we understand what others afford us, we've got this deep, evolved set of structures that are designed to maximize the likelihood that we survive and pass our genes along to the future generations. Now, I don't just say evolutionary, I say co-evolutionary, because in social cognition, it's going to become very clear that what's happened is not only do we have these internal parts that are looking for information in the world about what others afford us, but that we signal things to others, and we have all sorts of behaviors that are designed to signal things, and that these signals and receivers have co-evolved with each other. So that's the answer to this why coevolutionary. We've got evolution at the broadest time scale. We've evolved to have opposable thumbs. They're super helpful for wielding tools. That's an important part of what being a human is. We've also been biologically prepared to learn certain things and not other things. We come into the world as babies, and one of the things that we do is we have an instinct to look at what other people are looking at, especially our parents. So if someone walks into the room and our parents ignore them, we might not pay that much attention to someone new. But if someone walks into the room and they're wearing um, clothing that for our parents identifies them as a member of an out group, and they look at these people and they exchange looks with each other, as a baby, we pick up on that and we start to track these same social differences. It's also important for us to recognize that there's an evolution of cultural things as well. So there's biological evolution and then there's cultural evolution on top of it. And because we use language and we use tools, that component is really important too. So it's all three of these chunks that are critical to understanding how the human mind develops. Now, this is all broadly still within the purview of evolutionary psychology, but I also want to talk about the ecological perspective of James Gibson. Um, there are other people that have been called ecological psychologists as well, like Brunswick is a more popular uh, exponent of this viewpoint in Europe. Very often, Vygotsky is another one. Um, but we'll be using a lot of the Gibsonian ecological perspective because Gibson's the one that really talked about the idea of affordances. And so when we get into the in-person sessions, we'll be having a lot of back and forth, a lot of discussion about this perspective and how it applies to something else called smoke detector effects. Some of you have also heard of embodied cognition or extended cognition. There's a lot of overlap between these two perspectives, but don't tell it to the people that study both of them because they like to fight with each other and with us evolutionary psychologists. Um, but to me, they really provide they provide a really interesting counterbalance to the more evolutionary perspectives. And it turns out that out of the ecological and the embodied extended perspectives, um, you you get something called you get a way of understanding how cognition works that involves something called connectionism. You could just think about this as the philosophy that gave rise to artificial intelligence or neural networks. And this class is not long enough for me to really go into why these three things are related to each other, but I'll make some suggestions about why they are. It turns out that the people that do connectionism tend to be embodied theorists, tend to be ecological theorists. They often are quite resistant to evolutionary uh, or even cultural evolutionary perspectives. But ultimately, these are two ends of the continuum of processes that give rise to the online social cognitive experiences that pervade our everyday lives. What are we going to be doing in this class? Well, in addition to all this theoretical stuff that I want to introduce you to, I ultimately really want you to discover the power of creating a cognitive experiment. And we're going to use social content No one has to design a word recognition study, which would be something that's more purely a cognitive psychological experiment. We're going to use social content. So you're going to learn how to do this in a couple of different ways. As in most expert workshops, one of the ideas is for you to develop a project. And a lot of times what that looks like is showing you, or, giving you an overview of some field, and then you propose some sort of project. But often these projects, the expert workshop is on something that opens your eyes to some area, but it might not be something that you continue with afterwards. So you write paper after paper for these things, and that builds your portfolio, expands the way you think about how you can apply your skill set, but you're not necessarily picking up practical skills. Here, I really want I want to open your eyes to a whole new kind of research that you can do. So we're going to unlock the potential of how these social cognitive experiments can, first of all, leverage the power of within subjects designs. You can also call these repeated measures designs, and longitudinal designs often fit into this as well. So what I mean is, rather than bringing a subject in, having them turn wooden dowels for an hour, and then asking them, how boring was that? And discovering that if you pay somebody $20 to turn wooden dowels, they'll say that was really boring. But if you pay them $1 to turn wooden dowels, they'll say, it was actually not too bad. That's classic cognitive dissonance studies from Festinger in the early 60s. Instead of that kind of study, where you got to bring a bunch of subjects in cognitive psychology, we'll bring subjects in, and uh, you won't randomly assign them to one of these conditions, $1, or another condition, $20. You'll figure out some way to give them all of the conditions that you want. And you'll repeat that over and over again. And so this is a really potent way of designing research. And increasingly, I think this is going to be a skill that is going to make you really distinguished from other people that are competing for the kinds of jobs that are going to be emerging over the next 5 years. So we really want to open your eyes to this power of within subjects designs, and that means you have to develop a kind of conceptual understanding of what programming an experiment looks like. But I'm well aware that most people are not going to learn how to do JavaScript programming or anything like that. We live in a world now where that's not necessary. But unless you have the conceptual underpinnings of how to put one of these studies together, you can't vibe code it. I also want to use these approaches to open your eyes to how diagnostic inference, not deductive inference, not inductive inference, but something called abductive inference or diagnostic inference pervades everyday life. Those of you that are fans of Sherlock Holmes are probably familiar, even if you're not, you're probably familiar with the idea that the famous detective, when Watson would say, "How did you know, Holmes?" he would say, "Well, it's deduction." Well, in fact, what a detective is doing is not deduction, it's abduction. What Sherlock Holmes was doing was abduction. And the term that we probably want to use, because it's a little bit more comprehensible, is diagnostic. A detective uses clues to diagnose the cause of the crime. And that's what a social agent is doing as well. We see a look on another's face, and we make an inference about what's causing that. What is the internal state that that represents? Diagnostic inferences can be wrong. We might see a look on a person's face, and we say, well, that person doesn't look happy. They must not like me. Well, it could be the case that that person doesn't like something else. It could even be the case that they don't actually have an unhappy look on their face. They just have resting angry face. So diagnostic inference pervades all of social life. I would say it pervades almost all of cognitive life. The bulk of what we do as social and cognitive agents in the world, trying to survive, trying to thrive, is we use clues to diagnose and detect and make inferences about the underlying causes of others' behavior. So that's the kind of thing that we're going to be able to reveal with these cognitive methodologies. And we can do it in ways that are so subtle that, what's one of the fears that we have in social psychology that we'll assign someone to a condition and they'll figure out that we're actually trying to manipulate them with what we're showing them or what we're doing, and that will bias their performance. Well, in cognitive experiments, we're often looking at very subtle measures like how accurate they are at detecting things over many, many trials, or how fast they can do it. And so you can reveal things that are really hard to excuse away as some kind of social desirability or, conforming to the experimenter's desires. These effects are, they're very subtle. And so that's the beauty of these designs. And I want, by the time you're done, you're not going to be an expert in this, but you're going to suddenly realize how much more accessible it is that in a matter of a couple of weeks, you can learn how to design these things and open up a whole new world of possibilities for your research career. In order to do this, we're going to start learning the basics of signal detection theory, and we will begin today. In addition to the theory of signal detection, we're going to practice calculating key parameters of bias and sensitivity. And I will show you this starting in about 10 minutes. But by the time we're done, on Wednesday, we'll do some more detailed work with this. So on Wednesday, one of the nice things about doing this online is that you can watch this. I'll record it again, but you can also potentially, walk through the the work that we go through using a simple spreadsheet to transform hit rates and false alarms into these signal detection parameters of bias and sensitivity. The reason this is also important is because it illuminates a bunch of other things, like what we call smoke detector effects. And hopefully you read some of this literature already, so you've already got a kind of sense about where this is going. We're also going to introduce the additional inferential power of reaction times. And I'm going to introduce both of these things, but in between now or Wednesday and the in-person classes at the beginning of June, you will not only have one assignment in which you program an experiment using Open Sesame, which is an experimental design program that basically just uses, it's got this lovely interface and it just uses a spreadsheet to put together the design of a study. So you'll design this, you'll go through the first tutorial for this Open Sesame software. And that takes about 4 hours. And then you'll also conduct a signal detection analysis on some data that we collect on the classmate, on you and your classmates. So at the end of today's lecture, I'm going to give you 2 Qualtrics surveys to take, and they will have several different experiments in them. And do your best to figure out what I'm trying to do with it. I'll show you later that it doesn't really matter, and we can still get really interesting results. Even if you suspect what I'm trying to prove with these studies, and even if you think, I'm going to work in the opposite direction of this, I'm going to be one of those research subjects that doesn't want to be compliant. So you'll do an Open Sesame design in between now and June, and you'll also do a signal detection calculation on the data that we collect from this class. That alone will give you two skills that most other people in research master's programs outside of cognitive do not have. You will then design an experiment of your own. So you'll get these things. The earlier you get this out of the way, the easier it will be for you to design this experiment on your own. The best way for you to design an experiment like this would be a social memory experiment. But you can also, if you get really excited about the Open Sesame approach, uh, we'll do the first tutorial, but there's two other ones. And by the final one, it's starting to teach you how to use Python. So the early stuff, you're not really doing any programming at all. There's no coding. You're putting together a spreadsheet, you're dropping some images in. It's very hands-on. But if you want to push that skill set forward, by the third version, by the third tutorial, you're using Python to design something that's quite sophisticated. I do want to point out that Open Sesame was designed by Jan Theus at the VU. It is not an invitation to go down the hall and ask him to help you design this, though. It's mostly the students that he's worked with that have built this kind of thing up. But it's kind of nice to know that you've got a department in which there are quite a few people that already use this tool. And as I don't actually know yet, each year I offer to have students from the cognitive program in this research master's class. So it's possible that half of your cohort is in cognitive. And we'll figure that out because I've got questions about it in the survey that I'm going to give to you at the end of this. If you were in my in-person class and we were doing this as a full semester on social cognition, we'd be reading Fisk and Taylor's Social Cognition book. Here's the fourth edition. There's a fifth edition that will be out soon. This book is widely available, so you can find it used for 15 bucks. It's an incredible textbook. It's not even a textbook. It's like a survey of the entire field by two women who really were at the forefront of developing these approaches. Many of you have also heard of Daniel Kahneman, Nobel Prize winner, and his popular press book, Thinking Fast and Slow, is filled with really rich ideas that benefit from this signal detection frame. Finally, in my program here, I'm actually in both psychology and engineering. And a lot of what we think about is how we use how the design of humans influences how we design things, tools, social interfaces, experiences even that are designed for humans, and how we can better take into account human biases, flaws, how we can design things to be usable despite the cognitive and social and attentional limitations of humans. So the revised book, The Design of Everyday Things, is another really beautiful text. For those of you that really want to benefit the most from this, I realize that you're only getting this is only half of your credit for the research masters. You've got time, and I mean these are Thinking Fast and Slow and The Design of Everyday Things are both books that you can read in a day. Social cognition you kind of really need to dig into, but feel free to get these books. They're not required, but I just want you to know that these sit behind a lot of what I'm doing. Okay, so I think somebody just asked a question. I saw something pop up, so I'll stop for a moment and I'll ask if there are questions.
I just wanted to know if you're also going to be uploading the slides that you're using.
Ah, well, um, yeah, I suppose I can do that. I mean, the thing is, I've got I've got a ridiculous number of slides. I'm often, once we get into class, especially, I'm often uh jumping from one thing to another depending on interest. Uh but for these initial ones, I'll consider it. I mean, you'll have a video of this. Um the problem with my slideshows is I really heavily animate things. And so that is often a bit confusing. So if we pop out and look at the slides without having the slideshow going, there'll be big chunks of white on some of these screens because I've got a big white patch in front of something and then I fade it out so you can see it. So uh that's the one constraint with these. But yeah, I don't see why I shouldn't do that. And actually, maybe that would also be a valuable thing for you to understand is that PowerPoint can really be, or any sort of slide deck can really be a tool to guide your audience's attention. So for example, let's think about this is all from one slide. I'm gonna walk you through this animation. So let's get an example of signal detection. I want you to guess if a person is male or female from their height alone. So this person is 178 centimeters tall. Are they male or female? I won't in class I would have you like raise your hands if you thought they were male, but I'm not going to do that because I can't see. Um, so let's assume that the class generally says, yeah, that's a male. Someone who's 150 centimeters. Well, maybe people are more convinced that that's a female. So those are two inferences, diagnostic inferences about the underlying cause of a person's height, their gender, based on one piece, but it's just based on this one piece of evidence. You don't know what they look like. You don't know what their voice sounds like. You just know this one piece of information. So this clue is what you're using to make this inference. You're trying to diagnose gender from the effect height. What if we talk about someone who's not 178 but 173 centimeters? Well, probably still they're a male, but now you're less sure. Maybe more hands go up and say, well, maybe that's a female. Maybe you're a woman who's 173 centimeters tall, and you go, yeah. What about someone who's 162 centimeters tall? Well, maybe more likely to be female, but there's plenty of men that are 5'4". And so you're going to have less hands. You're going to have less hands going up at that point. All of these are what Daniel Kahneman and Amos Tversky would call decisions under uncertainty. We have a piece of evidence. We're trying to make a discrimination, male versus female. And yet we don't know anything else about the person other than their height. So there's a lot of uncertainty. And there's a chance that we're right, but there's also a chance that we're wrong. So in the world of signal detection, we think about this kind of graphic. On the x-axis, you have some kind of evidence axis. In this case, it's like an internal response. You are walking down the street, you see somebody in the distance. There's a light post there. The light posts are standard in your city. And so you kind of know based on the light post that this person is really tall or that this person is really short. So there's evidence that you're getting about the person, but are they male or female? You can't tell this yet. You only have evidence of the height. And you know that there's this distribution of heights of men and heights of women. So let's say that what we're really vigilant for is it's a dark street, it's late at night. We're really vigilant for whether there's a male walking down the street toward us because men are, they have more testosterone, which leads them to maybe be more prone to aggression. Men are probably also not as smart as women. They don't smell as good. There's all sorts of reasons you might want to walk cross the street and not be near this person. So male is the signal, and you've got this evidence or this internal response. And you know that the heights of men and women are like these two normal distributions that overlap, that men tend to be taller than women. So they're the part of the distribution in this image that's to the right. And then the other normal distribution for women is the one to the left. But it doesn't matter where you put your criterion, your response criterion, that line there. It doesn't matter where you put it. You have a chance of making a mistake. So yes, you might correctly say that's a male, but you might false alarm. And it might be a female. Or if you turn it around and you think, that female is the thing that you're really thinking about, but we're still going to call male the signal. Well, correctly rejecting a person as male, that's quite possible if a person is shorter, if the evidence coming into your sensory system is below this criterion point. But it's also possible that it's a male that's short, and so that would be called a miss. So we use the term hit and false alarm, miss and correct rejection to describe these different possibilities. It's important to note, however, that we really only need two of these. If you know the false alarm rate, then 1 minus the false alarm rate is the correct rejection rate. If you know the hit rate, 1 minus the hit rate is the miss rate. So we can use the term miss and correct rejection. We can use the term hit and false alarm. All four of those have meaning. We should be able to talk about them, but we really only need two of them, either the miss and the correct rejection or the hit and the false alarm, in order to figure out not only where this internal criterion is placed, but also how far apart the modes of these distributions are, how much they overlap. This is remarkable if you think about it. And I'm going to show you how to calculate all of this stuff. In order to do so, we don't need very much in the way of theory, except we do need to understand the normal curve. And all of you probably know this already, but the normal curve has these really beautiful symmetrical properties where, it's always the mode or the most likely, most probable response is at the center of the distribution, and that we can think in terms of the standard deviation. So the center of the distribution will be the mean. We can think in terms of the standard deviation, and we can transform any sort of proportion, this percentile down here at the bottom, we can transform this into something called a z-score. So between now and Wednesday, if you don't remember how these things work, just refresh yourself about what a z-score is. But for the purposes of this class, you probably don't even know that, because I'm going to show you the simple transformation that you do in Excel. So let's look at this height example a little bit more. We're thinking of male as the signal. That's arbitrary, by the way. Um, we could think of female as the signal. It just flips the terms around. Um, I want to point out at this point that I'm often calling this signal detection theory. That's the classical term that was used that comes out of the 1950s, 1960s, but it might better be called signal discrimination theory. Because here we have one piece of evidence, height, and we're trying to discriminate whether this is male or female. So let's say for one person, we give them a series of heights, like we did on that last slide. And when it's actually a male, 75% of the time, they say it's a male. But when it's a female, the actual sex is a female, 25% of the time, they're false alarming and calling it a male. Well, we can take that and we can transform it into a z-score. We can take these percentages and transform them into z-scores. Percentage above 0.5 is going to be a positive z-score. Something below 0.5 or below 50% is a negative z-score. And in a spreadsheet, we can like Excel, we can use a function. In Excel's case, it's norm S inverse. I believe it's also the same in Google Sheets. And that norm S inverse function transforms this percentage into a z-score. And then, and please don't worry if you're not quite getting this right now, because we're going to go through this several more times and you're actually going to hand calculate this. Then we can take these numbers, these z-scores, and we can combine them to get two measures, something we call sensitivity, or how much the distributions are separated from each other. How easy is it to tell men and women apart based on height? We can also tell where the criterion is placed. Is there more of a tendency to false alarm than you would expect based on the hit rate? So that's called bias. And in this case, when we calculate this, we get a sensitivity of 1.3, which in this particular case is very similar to the Cohen's d, or the effect size for a task like this. If you recall, a Cohen's d of 0.8 is a large effect size, so a Cohen's d of 1.3 would be a very large effect size. And in this particular case, there doesn't appear to be any bias to say male or female, one way or the other. So again, let me reassure you, if you're not understanding what sensitivity and bias are right now, or let me say it this way, if you are understanding it, then you already probably know quite a bit and you're going to do super well. But most people shouldn't quite be getting this yet. So if we remember this distribution here, what we're doing is we're taking this 75% and we're looking down here and we're figuring out where, between 50% and 84% here, where would 75% be? It would be about here. And we look it up on a table of z-scores and we pull out this number 0.674. We do the same thing for 25% down here, somewhere about here. And so it would be negative 0.67. And in order to calculate sensitivity, we subtract false alarm Z's from hit rate Z's. Subtracting a negative means really, adding a positive, and so that gives us that 1.3. And for bias, what we do is we add these two things together and we divide by 2, and that gives us a 0. Again, I just told you what the conceptual formula is for this. We're going to do it by hand. You're going to do it several times. You'll know this really well by the time the expert workshop is over. And you'll know why this is such an important thing. Because in the world of AI, a bunch of stuff that's going on is about signal detection. If you can talk about this, you can talk with people in the tech industry and really wow them. Now, for those of you that are good at statistics, you'll also know that there's lots of classification approaches and machine learning approaches to statistical prediction that do things that seem to be similar. And yes, indeed, a lot of the things in classification really come out of the early literature on signal detection. So you're getting an insight into a lot of really powerful tools with this simple example. Let me give you one more example, though. This is one person's response. They see, let's say, 100 heights, and 75% of the time when it's a male, they're right, and 25% of the time when it's a female, they make a false alarm. That gives us this contingency table. Let's look at another person. This person is right about it being a male when it's actually a male 75% of the time. But when it's a female, they're only saying male 10% of the time. Their false alarm rate is substantially lower than the first person. Well, when we look down here on this table and we look up 10%, we find where 10% would be. It would be about here. I guess it would be about here. But we don't look it up on we don't eyeball it. We use a statistical table to look it up. Well, for we already know that for 75%, that's a z-score of positive 0.674. For 10%, it's a z-score of negative 1.28. So that z-score has become more negative. So now if we subtract negative 1.28 from 0.674, we have a bigger number, 1.95. This person is more sensitive to making the discrimination between male and female based on height alone than this person up here, because they've got a higher sensitivity, and our measure of sensitivity is called D prime. Why is it called D prime? Well, historically, it's a great question. I think D just means discriminate or detect. But then the question is, why did Cohen use D for his measure of effect size? And I'm pretty sure there's a relationship here. We'll talk a little bit more about how Cohen's D is both very similar to this and sometimes can be quite different depending on how the experimental design is put together. But for now, just understand that the person at the bottom is more sensitive, can discriminate better between men and women. And that's a really valuable thing to know, right? If you're evaluating how well a person performs a task that involves discriminating, threats from opportunities, knowing how sensitive they are, knowing what their D prime is a very valuable thing. You can also use this for automated systems. You could look at AI. How good is AI at generating an image that can fool a person, a deep fake, let's say? Well, that's one way of asking the question, and you're asking how well a person behaves. But you can also take another piece of AI, another neural network, and you can see how well it can perform this task. And in fact, the GANs model, one of the more popular generative AI models, does exactly that. It has two components. One of them generates some image and tries to fool the other one, which is the discriminator. And you can use these metrics to understand how that discriminator is performing. More interesting than even that might be the fact that in addition to this person being more sensitive, they nevertheless show a slight bias to calling faces female. And it doesn't seem like that when you look at that upper row. But when you look at the bottom, you can see that 90% of the time they're getting females accurate. 25% of the time, they're calling males female. And so that shows that their criterion is not optimal. It's shifted over a little. For some reason, they're biased to say that there are more women than men. Now, maybe that bias could reflect where they come from. Maybe they grew up in an environment where there were more women than men. Maybe they came from, a place where most of the men have to go away and work in some other city. So it could reflect what they learned in their early experience. Or maybe they know that they're discriminating the heights of people, but all of these people are fashion models. And so they're biased to think that women are fashion models. And that may not be an incorrect bias. That might be correct. But in this particular case, we have an equal number of male and female fashion models. So their bias is suboptimal. I'm going over this example at length because I really want you to understand that the kinds of calculations that we're going to do, this is as complex as it gets. And it's very straightforward. And yet it unlocks all sorts of interesting possibilities. Now, in the second part of today's lecture, I'm going to get into some much more interesting examples, but I just wanted to ease you in with this. And so now what I'd like to do is I'd like to take a quick break. This will be, let's see, it's 5:30, or for you, it's 2:30 now. Let's take a 5-minute break. This is mostly just for me so that I can go blow my nose and use the bathroom, and then I'll be back and we will pick up with this lecture, and I'll take a quick moment to answer any questions, but a lot of your questions are going to be answered in the next part of the lecture. So don't ask too much about these calculations yet. Save those for later. Okay, so I'm going to stop sharing for a moment and I'm going to pause the recording. I'll be back in 5 minutes. Okay, I'm back. Are there any burning questions at this point, or can you trust me to get us to more interesting material than discriminating the heights, discriminating men and women from heights? Okay, I'll take your lack of quick response as a sign that I can keep going. Okay. So let's take this into an open sesame experiment. And this is similar to what you're going to be designing. Let's say that what we need to do now is discriminate F from M. A letter F is going to show up on one side of the screen, but it could be left or right, and on the other side there'll be this X. So you don't know which side it's going to show up on. In the Open Sesame tutorial, your task is actually to discriminate an F from an H, but we're just going to change it to an M, and we're going to give it a meaning. And the thing about this Open Sesame experiment that you'll design in the tutorial is it's based on a study called the Eyes Habit, in which before you see the F or the H in the original study, or the F and the M for us, you see this little smiley face that looks to the left or the right. And so here the smiley face is looking to the right, and but the X appears over there. That's not the signal that you're looking for. You're looking for an M. So hopefully you can quickly get your eyes over to the M. Well, it turns out that the eyes looking, it's something that I told you babies do this. Babies pay attention to where adults look. Well, according to the paper that the first tutorial is based on, and then in several additional studies that have been done that have replicated this, when you have an experimental design like this, where a happy face or a face is looking in one direction or another, even if the way that it's looking is not diagnostic of where the signal is going to show up. So 50% of the time, these eyes are looking in the direction that the M or the F shows up, and 50% of the time they aren't. There's just it has no predictive value at all. It doesn't matter how long you do it, people continue to look in the direction that the eyes are looking on at least some of the trials. It's an automatic instinct that we have to look in the direction that other people are looking. Some of you might know of the classic social psychology experiment by Bib Latané, where he would walk into a crowded part of New York, and then he would look up, and he would just stand looking up, and all the people walking by would start looking up too. What's up there? What's up there? There was nothing up there. He could just get people to look up because everybody wants to look where other people are looking. So this is a design that seems to be quite subtle, but you do this 100 times, a face pops up, it looks to the left or the right, and you start to realize that it takes people about 50 milliseconds longer to discriminate M from F when it shows up over here in the direction that's not being gazed at than when it shows up over here. Why is that important? That little 1/20th of a second difference seems like it doesn't have any practical consequences at all, but it tells us something really important about the design of the mind. And when you do it with 30 or 40 subjects, and every single one of them shows this effect, some will be bigger, some will be smaller. Or actually, maybe not everyone. Maybe 70% of them show it. Maybe there are some people that look in the opposite direction. Nevertheless, you've got increasingly compelling evidence that there's something about the design of the mind that has this instinctive guidance by the gaze of another. So this is a fundamentally social cognitive phenomenon. Where other people are looking, your eyes are also drawn. So this experiment has lots of different directions that can go. We could actually change the gender of the face. I think that this one has been done before. Not with this particular smiley face, but let's say you put a mustache on it. Now there's two things that could start happening here. One is that maybe some people are going to look in the direction of the male face more than they would look in the direction of a gender neutral face. Other people might look less in the direction than a gender neutral face because they don't trust where men are looking. So there's all sorts of things that you can start to get into. You might measure individual differences in the degree to which a person trusts men, and that might predict the size of the effect of this gaze direction effect. We can put an emotional expression on this face. Well, suddenly maybe that adds some kind of signal impact. Maybe we're more likely to look in the direction of a fearful face than we are a smiling face, because the fearful face activates our amygdala, which in part is a threat detection part of our brain. It activates our amygdala, and it motivates us to look in the direction that a person that's afraid is, because we might need to be afraid too. There might be like a spider or a scorpion in the environment. There might be a dangerous man. So all of these little tweaks, the same experimental design, all we do is change an image and run 50 people through 100 trials with that image, and we can start to see different effects. In both of these cases, we've got social information, gender of the face, emotional expression that the face is displaying, that are giving us additional information about what the environment is affording us. We could also have the face look in one direction and the eyes look in a different direction. That should dilute the effect. That's more of a purely cognitive phenomenon, but there's a social element to it. We could also have somebody that we really intensely dislike looking in one direction? Do we trust where they're looking, or do we look in the opposite direction? There's all sorts of possibilities with the same experimental design by manipulating the social information of who is looking. So here is the website for Open Sesame. So what you're going to do is you're going to download this and you're going to go through the tutorial. And I will let you know that, first of all, it's really important that you know that there are some bugs in this. And so this is a brand new thing. They now have this Sigmund AI thing that is better than ChatGPT for asking Open Sesame questions. But one of the things that will happen is that you will often get the large language models giving you the answer for how you design it with Python, because that's part of the way that Open Sesame works. So I'm going to make a discussion. As you go through this tutorial, I'll have a discussion space where you can ask questions and share strategies with one another. It's beyond the scope of what I'm doing for this expert workshop to answer all of your questions, but you can crowdsource among each other. And every time I do this in this class, people figure it out pretty easily. There are a couple of things that do happen. I think Macs work a bit differently than PCs. So you might want to be sensitive to what interface you're working on. And then the other thing that's really important to remember is that I guess this isn't just for Open Sesame, but for the signal detection as well. I'm often using English versions of spreadsheets like Excel, and in at least German versions of Excel, there are a couple of things that are a little bit different. So certainly the call to the function norm S inverse, or the z-score function that I use, that's different. So the discussion will be a place where you can figure all of this out. So this is going to be one of the things that you're doing in the interim between these online lectures and the face-to-face classes. So now let's get into some richer sets of ideas. Consider this simple task. Identify whether a face is angry or happy. This is from a JPSP paper that we published in 2007 at the beginning of my career. This is actually one half of my dissertation, and it's been cited a whole bunch now. So some of you probably already know it. It's in a few of the textbooks. So we showed them these classic Ekman faces, male and female faces. So this is a discrimination task, just like height, but now I'm giving you much more information, right? Uh, I'm giving you a face and it's moving. It's got these different features, and the task is discriminate angry from happy, but I'm showing you male and female faces as well. So we could ask the question, how does the masculinity or femininity, apparent masculinity and femininity of the face affect these decisions? And when we do that, we can look at both accuracy and reaction time. So I give people this study. It's very similar to the Open Sesame study, but it's actually even simpler than the Open Sesame tutorial. You just show one face and you have people hit one button if it's angry and one button if it's happy. But I do it with 6 male and 6 female faces, each one with a happy and angry expression. I repeat each one of these 6 times over the course of the study. And so you end up with a lot of trials, and you can calculate hit rates and false alarm rates over many trials. And you can also look at how fast they're making these decisions. Well, when we do this, or when we did this, we can first look at the hit rates. People are quite good at detecting angry men, the anger on men, but they're a little bit less skilled at detecting anger on female faces. In the converse condition, looking at happy faces, well, it turns out that people are faster they're more accurate at detecting happiness on a female face than a male face. Now let's look at reaction time. This is reaction time in milliseconds. Turns out that people are much faster, well, much. They are statistically significantly faster to detect anger on a male face than on a female face, and they're statistically significantly faster to detect happiness on a female face than a male face. So let's take a moment and think about what this means. Both accuracy and reaction time are showing that people seem to be better with angry men and happy women. That when anger shows up on a female face, it not only reduces accuracy, but it slows people down. When happiness shows up on a male face, it not only decreases accuracy, but it slows people down. So this is two different measures in the same study that are revealing a kind of, well, I mean, the first hypothesis that comes to mind and that came to our mind is that this is a stereotype. We have a stereotype that anger is more likely to be a masculine emotion and happiness is more likely to be a feminine emotion. And so that means that we're biased to see happiness on female faces and anger on male faces, and we're also quicker to make those decisions. Now let's talk about another recent study that we did. In this study, what we did was we showed male and female faces, but we blurred them. We used what's called low pass filtering, but you can just think of it as a blurring manipulation. And this is an interesting kind of manipulation because it's both something that cognitive psychologists and human factors researchers use because they, for a long time, it's been really important to figure out in practical applied settings how visual degradation affects performance. So a pilot flying through fog, we want to know, how well they can see the lights on the landing strip, that kind of thing. So we blur the faces using a JavaScript blur function. It's a basic part of JavaScript. And what this does is this makes the task of discriminating anger and happiness harder, and it may actually increase the likelihood that we rely on stereotypes, but maybe it doesn't. Maybe it makes it better. We'll find out. So we have 3 new studies in which we've manipulated how much the faces are blurred. Here we're using the Radboud expression stimuli, which I think are a little bit better than the classic Ekman ones, at least from the perspective that there are more of them, and they're more diverse. But from an experimental perspective, we also want to use other faces because that allows you to generalize the effects to a new image set. So it's a task that looks like this. What is the expression? And you can say to yourself what you think it is. My guess is that many of you under this level of blur can look at this and will say that that's a happy expression. I should also maybe ask you the converse question. Is this a male or a female? You've got some evidence. It's not height anymore. Now it's like sort of this blurry set of facial features. Is this a male or a female? Here's an even more blurred face. Is that angry or happy? Is that male or female? Is that the same individual or not? Here's another face that's even more blurred. Is that male or female? Is that the same individual? Is that angry or happy? We're constantly making decisions under uncertainty. And in social cognition, we can crank up the uncertainty with a manipulation like this. And that can be a really valuable experimental tool. Maybe as people become more uncertain, the biases start to become more clear. So here we're going to focus on accuracy. In the first two studies, we didn't even measure RT. I do have it. RT is reaction time. We do have reaction time in the final one. And then I've replicated this again since I last had this, prepared this slide. So here we just focus on accuracy and we focus on hit rates and false alarm rates, but we'll translate them into those signal detection measures. So here's the second of these studies. Here, expression discrimination is still possible or manageable, even with that most blurry condition. So here I've got the D primes plotted, and any positive D prime, anything above 0 tells you that people can discriminate above chance. Well, actually, statistically, you could test that, right? You could look at the confidence interval, the 95% confidence interval around any of the points in this graph. And if that 95% confidence interval does not overlap with 0, then that's equivalent to doing a t-test and saying that it's significantly different from 0. So people can still perform the expression discrimination task even when things are quite blurry. But you can see that the increasing levels of blur from 6 pixels to 8 pixels to 10 pixels, well, the more blurry it is, the less discriminating they are, the less successful they are. Bias, on the other hand, yields a much more complex picture. So now, I want you to focus on the 0 line, which is the third line up. That is an unbiased performance. And so when we look at the 6 pixel blur condition, you can see that there's a general trend to call faces angry. I'm sorry. When we look at the 6 pixel faces, there's a general trend to call faces happy. And then as you blur them more, that bias shifts more to anger. So the less certain we are about an expression, the more blurred, the less evidence we have, the more we shift to having an anger bias. And here again, you can do the same kind of thing. You could compute a 95% confidence interval. You could see if it's statistically different from 0. Having looked at this and used this in many lectures, I can tell you, I should actually have the confidence intervals on here, but I can tell you that there is a significant bias in the 6 pixel condition, a positive bias, which in this case means it's identifying the face as happy. That at the 10 pixel, even though the linear trend is statistically significantly negative, so it runs from happy to angry. At the 10 pixel point, those points aren't statistically, the simple effects there aren't statistically different from 0, except for male faces in the 8 pixel condition. There is a difference. It's a significant bias to see anger. So now let's think about this. What I'm doing is I'm not just plotting the overall bias. I'm plotting the bias as a function of whether the face is male or female. They're not even having to process whether it's male or female. But here you can see that the masculinity or femininity of a face is affecting things. And when you have an 8 pixel blur, presumably that's a point at which you've lost a lot of the information about the expression, but you can probably still discriminate male from female. And so it's the fact that you're detecting that it's a male face is really biasing you to see that face as angry. And all of that is relative to this 0 line, which is an unbiased line, or the line of unbiased performance, of optimal criterion placement is another way you can think about it. So you can see here that the only statistically significant bias to call a face angry occurs for males under 8 pixel blur, but with 44 participants, it does yield statistically significant T, and more importantly, the Cohen's D is 0.32, which is a small effect, but it allows us to conduct a power analysis and I mean we don't really need to because we've already got the effect, but in designing future things, um, that effect estimate gives us some new leverage to think about what the effect size is as we tweak this design and how many subjects are we going to need to continue to reveal whether these effects sustain themselves under other manipulations. What about identifying gender under blur? Well, it turns out in study 2, we also then asked them identify the gender. And so here you can see that discriminating male from female. Now I've got the lines broken out by whether it's an angry or a happy face. So you can see that male and female discrimination also is better with 6-pixel blur. It gets progressively worse as you get to 8 and 10-pixel blur. There is a bias to identify the faces as male. That's true for both angry and happy faces, but you can see that there's a big difference. Much more likely to call an angry face male, which means sometimes angry females are being called male. So the gender discrimination is good. There's a general bias, but we're much more likely to call angry faces male, and that effect is generating a Cohen's d of 0.93, a large effect size. At this point in my career, I've done this so much that I'm pretty sure it's a real effect. We've seen this bias to call angry faces male and to call male faces angry in probably 50 studies, and there's another 100 in the literature. So this is a really strong bias. Thus far, our explanation for this bias is only stereotypes. So maybe just a couple of you, maybe I can ask the class, what are some other possibilities besides stereotypes? What might lead to this bias?
I was thinking that it can be about threat.
Yeah, so maybe what we're really picking up on is a connection with masculinity and threat. Um, and that might not be a stereotype. That might be a real, that might be a real connection. So my colleague Doug Kenrick in the early days of this was really thinking that maybe there's just this deep instinct. It's not a stereotype at all. You could find people that are raised by angry women and passive men, and they'd still see this effect. So that's a good possibility. Anything else?
Maybe it's just a physiological difference that the features of a male face are a bit sharper and harsher, and then when it gets blurry, it just looks more like an angry face.
That is a really good thought. I mean, all of these things are true, but what you're getting at, Giovanni, is why we think in terms of coevolutionary psychology now. Maybe the sharpness of the features is something that the system just automatically picks up on and has related this. Now, the other possibility is that maybe the sharpness of the features leads to this masculine detection, but why would it affect anger? Well, another possibility that Narayana Srinivasan and I published in 2014 in Perspectives on Psychological Science, though it really, I mean, the initial claim was made in this 2007 paper, is that it's quite possible that the angry and happy facial expressions actually evolved to mimic some of these features. Why are we the only, most animals, when they show their teeth, they're not expressing happiness. They're telling you, get away from me, I'm going to bite you. Why do we show happiness with exposed teeth? Um, that seems to be using a signal, a clearly discriminable contrast between the white of teeth and the darkness of the skin or the darkness of facial hair to signal something that's quite different than the way most animals signal things. And the same is true of the expression of anger. Why do we lower our brow when we're angry? Maybe that makes the face look more masculine. So all of these are possibilities. Let me give you another example of a signal detection task. This is a study that we've now, I think this is moving into, I think we're submitting this. It might even be under review. Chala and Josh Tiber, you might know both of these folks. We're interested in, so we've been talking about biases to perceive something. What about biases to remember something? So we gave participants a bunch of images of familiar and unfamiliar foods, and it also varies by whether they're plant-based or meat-based foods. And so here are some examples. Those delicious looking gnocchi up there. That might not be the best example. We didn't actually use this one, but those are actually grubs, which are delicious and nutritious to many people in the world, but a lot of people in the developed countries aren't as keen on them. Escargot, well, that's high cuisine for many, but most of my, I come from Appalachian country, and so most of my redneck relatives think that French cuisine is totally gross because escargot seems really disgusting to them. There's some unusual fruits and vegetables there too. So what kinds of things what kind of inferences do we make when we see familiar and unfamiliar plant and meat-based foods? Well, we can not just show them that and ask them what they think. We can show them these images, and then we can show them a picture of a person, and that person tells them what the food was like. Oh, that food was great. Oh, that food made me sick. So now we've got a piece of social information coming from another social target or from another person about the quality of this food. And so instead of detecting whether the food has pathogens in it or not, we can look at how biases in memory for what people say about the food arise. And this illuminates perspectives like social learning. How influenced are we by the things that we learn about the world from other social agents? So we show the people foods, we show the people a person who ate the food, and they tell you whether they got sick or whether it was good. And then we ask participants showing the same foods again, whether this food made someone sick or not. Not whether they like it or not, but whether it made someone sick or not. So what kind of hypotheses might we make here? One hypothesis might be that people will be better with familiar versus unfamiliar foods. When I say better, what do I mean? I mean that they'll be able to discriminate better between memories of whether the food made someone sick or not if it's familiar. But in fact, maybe they're not. I mean, maybe one of the things that happens is that we use our own biases there. I don't need to have somebody tell me that escargot made them sick. I know it's delicious. I love it. So I might remember that it didn't make someone sick because I've had a lot of experience with it. So familiarity in this case might actually lead to bias. It lets stereotypes intrude. What about unfamiliar foods? Well, maybe in the case of unfamiliar foods, maybe there we're motivated to pay more attention to what another person says because we don't know what that food is. So maybe we'll be more sensitive in that case. What about biases? Well, we might also be biased to remember familiar food as being good and unfamiliar food as making us sick. Or it could be more complex. Maybe it's going to be moderated by whether it's plant-based food or meat-based food. Here are the results. So I have whether it's meat-based or plant-based in the columns. And then I have what people said about the foods, whether it was negative or positive. That's the first column. And then the second column is whether it's familiar or unfamiliar. And so here we're going to treat the categorization as positive as a hit. This is generally an arbitrary thing. We figure out what signal we want to call the hit and what we want to call the noise. In this case, we're going to say remembering something as a positive outcome is the hit. So if things were positive in the familiar, I'll just go through a couple of these numbers. In the familiar condition for positive food, 88.6% of people remembered meat as being positive, so they hit. And in the plant-based condition, it was 88.1%. Those probably aren't different from one another. In the unfamiliar condition, yeah, we also see pretty similar results, but people are hitting less. They're less accurate in this case, in the unfamiliar case. So 76.4% for meat-based unfamiliar foods that were positive and are correctly remembered as positive, and 74.4% for plant-based foods. What about if a person reported a negative experience with the food, though? Now things get a little bit more interesting. In the plant-based condition, we have 23% of people who saw a food and it was reported as being something that made someone sick. They're false alarming and they're saying it was a positive outcome, even though it was a negative outcome. And in the unfamiliar plant condition, 25% are misremembering negative outcomes as positive outcomes. That's not showing a great deal of sensitivity, and that's not a very good bias, right? We should be remembering the things that might poison us. When we look over at the meat condition, the numbers are a little bit different. For familiar meats that were negative, that led to negative experiences, people are false alarming and remembering them as positive 26% of the time. But for unfamiliar meats, it's only 15% of the time. Now that's a bit hard to wrap your head around when you're looking at hit rates and false alarm rates here. Why would there be a reduction of false alarm rates for negative, unfamiliar meats? This is one of the reasons why we want to learn how to transform these hits and false alarm rates into signal detection metrics of bias and sensitivity. So we will do this here. I've gone through the intermediary steps of transforming these into z-scores and doing the calculation. And I'm just going to focus on the bias to remember something as positive. Well, you'll see that there's generally a bias to remember things as positive for familiar items, whether they're meat or plants. There's no bias, it's almost zero for the unfamiliar plants. But for the meats, there's this negative bias. And what that really amounts to is a bias. It's a negative bias to remember things as positive. So if you work your double negatives out and work through the logic of that, what that really means is that there is a bias to remember unfamiliar meats as leading to negative consequences. We can plot that here, and you can then put confidence intervals on there, and you can test whether that bias is significantly different from zero or not. Or you can put all four of these measures in a repeated measures, and you can run the interaction test. So it turns out the interaction test is highly significant. The simple effect is marginally significant for unfamiliar meats. And so after, seeing unfortunately a marginally significant simple effect, we doubled the number of simuli, replicated the effect, and found a significant bias. We can also look at sensitivity if we want. It does look like people can perform this task, so they have memory sensitivity for whether things made people sick or not as a function of whether they were familiar and unfamiliar meats and plants. But the lowest sensitivity is for the unfamiliar plants. That might be interesting. So this all gives us an insight into something called the smoke detector principle, which is something that my colleague Randy Nesse here at Arizona State came up with when he was still, I think he was at University of Pennsylvania at this time. And he was founding the field of not evolutionary psychology, but evolutionary psychiatry. How can doctors who are trying to diagnose mental disorders, how can they think about these mental disorders like anxiety as being an overactivation of very adaptive biases that our ancestors would have had? So Nesse's smoke detector model essentially says it explains why evolved systems that regulate protective responses often give rise to false alarms and apparently excessive responses. Nesse cites many psychopathological examples. So you can think about anxieties, which lead individuals to overperceive social criticism. There might be a male face that's looking neutral, but we know that people already are biased to see that male face as being angry. And a person who's socially anxious might be particularly biased to see it as angry. We might be overly biased to see aggression in members of an out group as opposed to members of an in group, all other things being equal. Obsessive compulsive disorder, in certain cases, it's about worrying about pathogens, and that could be an overactivation of mechanisms that, when they're working efficiently, do protect us from contagion risks. So Nesse talked about false alarms to see threat where none might exist, but we can also extend this to opportunities. Marty Hazelton and David Buss, two of the big names in evolutionary psychology, they used a similar logic in their error management theory to explain why men, when they're dating, often overperceive the interest of their dating partners. How'd your date go? Oh, it went great. She loves me. Maybe she never calls again. But that's where the bias for men is, and they think that it's because there was a big cost to missing signals of potential interest, and that cost outweighed outweighed the costs that go along with over perceiving interest. Now that might be debatable. Certainly today, in the richer social ecologies that we're in, if you misperceive someone's interest, and especially if you're a male and you hit on them, it might have negative consequences. So those biases could be shifting. But in their error management theory, this is the way that they specified how these biases would work, and they had some good evidence for it. So whereas men might overperceive interest in potential mates, with women, they've documented an underperception of a mate's willingness to commit and invest. Now they did it with men, but Brad Sagarin and I, in the early days of both of our careers, we tried to apply this to non-heterosexual relationships. We also did this with Buss's jealousy difference that he observed with heterosexual men and women. And so the picture can be more complicated. And that's another thing we can do with social cognition. We can take these classic general effects and we can start testing whether they apply in new sub divisions of the social milieu. Now, the work that I'm going to have you read of mine, you've probably already looked at the reading list and seen that there's quite a few things that I've done. But my work really ranges pretty broadly across all the different levels of information processing. And we've repeatedly been able to show with experimental manipulations that you can experimentally induce biases, even in simple detection tasks. So if we're thinking about over-perceiving social criticism, maybe I can have people play a game called Cyberball, where they are playing a game virtually with someone else and a couple of other people, and all of a sudden the other people start playing the game with each other and excluding that person. That activates a sense of fear that I'm being ostracized. That might make me in a subsequent detection task much more likely to see faces as disapproving than approving, because that bias maps onto my recent experience. You'll also read a paper called Signal Detection on the Battlefield, in which we have people try to detect whether they see a brief flash of an insignia that indicates whether a person is an enemy or a friend. And that when you manipulate the emotional state that a person is in, you can push those biases around and increase the likelihood that they detect enemies as opposed to friends. But it's always calibrated by other social information in the particular trial. So I commend that paper in particular to you. It's in +1, so there's no paywall. You can read it really easily. And it's a good example of how you can use experimental manipulations to push biases and even sensitivity around. That's an important point. In social cognition, we often look at biases, but sensitivity has received little attention. And so we can give several examples of sensitivity. So once again, I want to return to what the deliverables are going to be in this class. I've given you a sense of sort of where we're going, but there's many more paradigms and designs. There's much more theory, much more content that we're going to look at. But just to remind you that you're going to be learning how to do these signal detection calculations. So that's a super practical skill that you can apply all over the place, and it's going to make it a lot easier for you to talk to people in the tech world about classification algorithms. You're going to program the eyes have it study, and then we're going to do a number of other things. Because there's 30 people in this class, maybe we can't do as many things as I thought we were going to do. But one possibility is that we do a 5-minute talk. So you'll do an in-class presentation, but a 5-minute talk that you record and post to the web, and then we can have other classmates view. Let's say I randomly assign you to view 5 of them, and you evaluate each other. That is, I'm trying to come up with methods for this class that are scalable, because this class is twice as big as last year's class, and my paycheck is not twice as big. That's okay, because I love teaching this, so it doesn't matter. But I am trying to think about how to make it scalable as the research master's programs are redesigned, so that it's something that we could offer to all of the other research masters as well. Okay, so now I said that we'd only do 2 hours, but we're going to have to take another quick break because we're not quite through with what we need to get through yet. So let me stop sharing for a moment. And are there any general questions right now before I run off and get more coffee? Okay, I'll take your silence as an invitation. I'll be back in just a few minutes. Okay, let's continue. So let's now adopt a broader perspective. Social cognition is about applying cognitive experimental methods to social problems. We've already discussed this. So you don't have to know a lot about cognitive psychology, but it's a good idea to kind of know that there's this broad sort of model. This is the Atkinson-Shiffrin model of how things get into the system. There's a stimulus out in the world. It gives rise, it gives rise to some sort of information that hits the sensory organs, and then somewhere between the sensation and the further processing, we have this perceptual process that goes on. The definition of perception is quite variable, but it's a kind of selection and filtering process generally. There's an early component of this that governs the kinds of things that go into sensory memory, which is this super brief memory that you have. We won't really be talking about sensory memory. That's hardcore cognitive stuff. But when you start paying attention to things, that can move things into short-term memory, or you may have heard the term working memory. Short-term memory is sort of like a capacity, whereas working memory is not just that storage capacity, but an ability to manipulate things. And that memory is really interesting to us because it is the bottleneck that moves things from your perception of the world into the knowledge structures that make up your internal landscape. If things are maintained in working memory successfully for long enough, then they're encoded and consolidated into long-term memory, and we can have memories that last days, months, years. We can look at how repetition can improve working memory. We can look at how different retrieval cues can facilitate getting things from long-term memory to back into working memory, and then you can make some decision about it. Forgetting shows up. So there's all sorts of different levels of processing that we can look at. We're really going to be focused on attention and long-term memory. But it's worth knowing that these other aspects are part of the model. So another way we can think about things is as a flow from a pre-attentional stage into attention. And when we attend to some things, so I look at the eyes make me look to the left or the right, I attend, and then do I encode what I look at? Or do I understand that I have to encode that it's an X to move my eyes to the other side. So how long does that encoding last? Does it allow me to move things into short-term memory, which you can also call primary memory or working memory? Do things then move into secondary or long-term memory? The term primary and secondary memory, those are terms from William James. I probably should not be using those anymore. That is, it's still a valid distinction, but it's not often used. And once you get into secondary long-term memory, then you've got these knowledge structures that you build up that govern how we judge others and govern the kinds of behaviors that we engage in. So stereotypes sit in long-term memory, but they influence judgments and behaviors. Now, this seems like a one-way flow of information, but in fact, it also flows in the other direction too. Judgments and behaviors affect what we attend to and maybe even what we pre-attend to. So we can use this model to ask questions about how we process social information, how we process threats and opportunities. We can ask, is there a deep structure to what we detect and what we miss? One of those deep structures is that when eyes are looking in a particular direction, it increases the likelihood that we detect things in the direction of gaze and that we miss things that show up in the opposite direction. We can ask, how does this depend on our ecology, the environment that we are in? How does it depend on the environment that we encountered in the past? How does it depend on the things that we encoded in the past? We can ask how we mentally represent these social categories, these differences, these threats and opportunities. Long-term memory isn't just like a computer memory is a bunch of stored locations, but you can have things stored all over the place. When you defragment your computer to save space, what you're doing is the computer can save stuff all over the place. So you can have a book and chapter 1 is saved over here and chapter 2 is saved over here by stuff where you have your images of your last vacation. And everything is indexed in a way that it doesn't really matter what the location is. But the way that we store information in long-term memory definitely has a kind of map-like structure to it, or has a hierarchy in some cases. So there are these structures of knowledge that are really important to how we represent differences. Structures of knowledge also include things like stereotypes and, more broadly, schemas. You have a schema, an idea of what a psychology professor is going to look like and do in their spare time. So your perception of your psychology professor probably involves them, maybe being bald and wearing glasses. That's a kind of eggheady stereotype. Um, you know, one of the stereotypes we used to have is that professors smoked pipes and had tweed jackets with patches on the elbows. And when you ask, well, what's a professor do in their spare time? You tend to think, well, they probably go to the symphony and maybe, what do they drink? Well, they are more likely to drink wine than beer. All of these are ideas that are encoded in structures in our mind. And then when you discover that your professor plays in a rock and roll band and DJs ecstatic dances, that violates the expectation. Suddenly, you know, this either becomes a new category, it calls for a new category because your stereotypes have been violated, or you might suddenly start thinking that, well, maybe this person isn't really a professor after all. Should they be doing this? Are they really uh, competent to teach this class? All sorts of things happen whenever our schemas, our stereotypes are violated. So all of this has to do with mentally representing these differences. And as I just demonstrated, all of this affects how we judge and make decisions about things going on in the environment. So traditionally, cognitive science has emphasized really simple stimuli to study basic processes. So the first 30 years of cognitive science use stimuli like this. You'd show people these really simple, controllable stimuli. You'd let them react to them. You'd look at the decisions that they made and how fast they could make these decisions. And that gave us a great sense of these basic processes. This is attention. This is working memory. This is long-term memory. And if you read a lot of the early thinkers, or if you read Howard Gardner's wonderful 1984 book, The Mind's New Science, it still has not been eclipsed, I think, in terms of a beautiful introduction to cognitive science. And I've got the PDFs of it if you would like. I can make them available. He said that one of the things cognitive science did, because it was drawing from not only psychology, but anthropology and linguistics and computer science, was they decided that they were going to investigate the pure processes of thinking, and they were going to leave emotion and social complexity out of it. because they wanted to look at processes without having these other messy, noisy factors in there. It was an experimental control strategy. But when we ask what the brain was really designed to do, well, in the real world, the cool reason that we encounter in the laboratory is a very special case. And in fact, the majority of cognition is very hot, very engaged. The objects that we encounter in the environment are not these blue triangles or these Navon interference patterns. They're saturated with history and social context, and they give rise to emotions. And so that's what I've done with my career. I was trained as a cognitive scientist, but very early on, I thought it's time for us to stop bracketing the emotional and social complexity and really start looking at it. So what is this social heat? I would actually argue that the early cognitive scientists, they were quite right in focusing on process, but they made a kind of mistake in not recognizing that the very existence of our advanced cognitive abilities, like attention, working memory, knowledge structures, the ability to use language and categorize, classify, reduce a person to a set of labels. Oh, that's a Lithuanian engineer. That conveys a kind of information that already activates a bunch of ideas in your head. Our cognitive abilities were selected not to solve the kinds of problems that the laboratory cognitive scientists are throwing at them, but to solve social problems. Our cognitive abilities are driven by our highly social nature. And in fact, Robin Dunbar has made this case in his social brain hypothesis. We can go so far as to say that social sources of information, like signals in the human face, are more fundamental kinds of stimuli, both phylogenetically and ontogenetically, than the simple stimuli that are often used in cognitive studies. So much of cognitive psychology has looked at letters and words, which is really important, but we're not designed, millions of years of evolution occurred before we had letters and words. We did have faces looking in directions, making angry expressions, throwing rocks at us, or opening their arms and wanting to give us a hug. So perceiving, attending to, and remembering faces, it's not clear that is reducible to the processes that are revealed by simple stimuli. So a real angry face might generate results that are quite different from some simplified version of an angry face. And in fact, this is the other part of my dissertation, which was also published. So my dissertation was published in 2 different pieces, and they're quite different. Both of them are really well cited too. And so some of you know about this research as well. Detecting angry faces in crowds of faces. So I've made the case that we really need to start thinking about social cognition as maybe the ground of cognition. But as we go forward, we also need to recognize that social cognition, and more specifically signal detection, requires the precision and strong inference of the cognitive methodologies. So that's what I want you to really get out of this class. Not only a sense of what social cognition is and the broad range of questions and problems that we can investigate. And you saw that in the Oxford Research Encyclopedia article that I assigned for this class, but I've also got one on social inference that I wrote with Klaus Fiedler and Christian Unkelbach. And both of these really cover the range of social cognition. And throughout, what you'll see is that the way that we do social cognition correctly is to get these cognitive methods dialed in precisely, and then we just change the stimuli. So let me give you, actually, I think this is a great point to stop at. Let's stop here. Hopefully I bored you in the early part. Maybe I frightened you a little bit, and then I got you kind of intrigued. Okay, I can maybe do those calculations. And then I gave you a few practical examples, but you were still thinking, how broad is this? Now I've talked about some bigger sets of ideas. I'm assuming that many of you may not have read the Ratner social cognition piece. So now I think you're in a good position to start getting excited about the breadth of the content that we can engage in. You've got the ability to go off and check out the website for Open Sesame. And on Wednesday, when we meet again, I will have data and we can go through some signal detection calculations and really get started. And then I'll close that with some additional information about some other research ideas that I'll really try to open you up to the different research possibilities. Because right now it probably seems like this is really focused on how do people perceive faces, but these questions can be applied, or these approaches can be applied to anything. How do we make attributions about whether a person's behavior is driven by the situation or by their internal design, whether that's something that was learned or deeply evolved processes? We can look at stereotyping and prejudice, as I've already noted. We can look at how affect and cognition interact. That's a big part of what I've done. We can look at influence. We can look at how intergroup processes work. We can design things so that we use basic social motivations to improve the way that a system works, or to at least understand the biases so that we can better design systems around those biases. There's just an incredible range of things. In most programs, most graduate programs, like a PhD program, you'd actually have at least one semester that's all devoted to the social cognitive research. And then another that is devoted to you'd probably end up having one class that's devoted to the classic research and another that's devoted to methods. And so I'm giving you just a very little taste of this. But by the time you're done, I want you to really be able to think about how broad the field is, how you can apply it to anything. So I know, having worked with the people at the VU now, I know that some of you are going to be really interested in conspiracies. How do people pick up information about conspiracies? Is their attention drawn to these salacious things that might underlie a conspiracy? And why do they then go and pay a lot of attention to that and preferentially share information? Some of you are interested in close relationships. How do people track whether their spouse or partner is pleased with them or not, and things are going well in the relationship? There's all sorts of subtle facial cues. There's all sorts of interpersonal things that can happen, and these things can shift over time. We can both be biased to see our partners as better than they actually are. In fact, Stendhal, the German philosopher, had this theory of love that basically amounted to saying, in the early days of love, we idealize the loved, the beloved, and we're biased to see everything that they do as wonderful. And eventually, though, you start to, see through that, and the crystal palace that you build around this person comes crashing down. Maybe successful relationships are a function of people having greater sensitivity to when there's distress in their partner, but not overly false alarming. You know, it's totally annoying to go out with someone who's constantly worried about whether you're upset about something or not. So signal detection parameters can influence that. If you're working on pathogen avoidance or aggression or social cooperation or ostracism, um, all of these things involve the kinds of processes that we're going to be investigating. So there's just a rich terrain ahead of us. So now what I want to do is I'm going to give you time to ask some questions. Um, and then I'm going to send an announcement out with 2 surveys for you to fill out. I need to make one change because I want to be able to link the two together. So I have to give you some way of identifying yourself, but I do want you to go through this and not feel like I'm analyzing what your responses are. So you can just make up your own code. You can use a 5-digit number, you can use a word, it doesn't matter to me, but use the same thing on both of these. Um, Actually, let me think about this. Uh, no, actually, I think I do need to know who you are, at least for one of them. Um, but I mean, we're not going to publish this, so don't worry too much about how you perform on this. Try to do your best because I'm going to ask you basic questions about how. Um, I'm going to ask you basic questions about what your background is and how prepared you are and what your goals are. But then I'm going to give you multiple little experiments. And we'll be able to play with those experiments both in Wednesday's class and then whenever we get in person, once we're in person, I want to be able to walk around and really help you to understand how to get into uh, these data sets that result from these experimental designs. And the ultimate goal will be that by the end of the class, rather than just having another research paper, which are a dime a dozen these days, and in the age of generative AI, increasingly less valuable. Um, I mean, they're intrinsically valuable, but they're less extrinsically valued. You're going to have skill sets that are irreplaceable. You're going to know how to talk about things in terms of signal detection and classification. You're going to know how to talk about social cognition and big theories like evolutionary psychology, affordance management, embodied cognition. And you're going to know, moreover, the directions you have to go to really continue to build those. So many rich, rich books, so much beautiful literature. This is like, to me, this isn't like a typical science. You might love rocks, and so geology is a great science for you, but other people don't love rocks. You might love space and you become an astrophysicist, but other people, they look up at the stars, they're like, yeah, that's pretty, but I don't really need to know how gravity works. With social cognition, everybody is interested in how people function, what guides them, what drives them, and what makes them make mistakes. So this is a potent set of skills, and the literature is just filled with fascinating things. This class is designed to open you up not only to the ability to look at that literature and really appraise it in a sophisticated way, but to understand that you are capable of doing this. And that there's going to be, I think, in my opinion, there is going to be immense opportunities, especially in the tech world, for people who understand how these processes work. There's a great talk that I give my students from one of the big tech expos a few years back, where a guy from Google talks about how pretty much everything that's happening at Google is based in cognitive science. And if you know cognitive science, you got an open door there. And this is even more true now in the age of generative AI. They have plenty of people that are learning how to do the programming, but not a lot of people that understand the human centered and usability side of things. And even in human-centered and usability research, there's a lot of people that don't understand social cognition at all. I know. I'm in one of the programs that produces them and is highly rated, and we still have a bunch of people that come out not really knowing the social cognitive stuff. It's incredibly valuable. And so I look forward to what you're going to discover. I envy you the discovery process that you're about to engage in. So, I'll have two surveys that I have to send out. But now let me stop sharing, and I'm also going to stop recording so you can ask questions and not feel like they are going to be memorialized forever. So thank you for your attention. All of this will have been, I'll post this to my YouTube page and then I'll give you the link so you can review this. I'll do that right after this class. But let me give you a little bit of a chance in the remaining 37 minutes to ask questions. We don't have to take all this time though.